Twin rig trawling has had more influence on the UK fishing industry than any other fishing method of modern times. Multiple rigs in general have been used for many years in several overseas fisheries to target specific bottom living species. The marine technology group based at the Seafish flume tank in Hull answers a regular flow of inquiries about fishing gear. Most of these inquiries have involved twin rigging. Despite the newfound popularity of twin rigging and its success as a fishing method, there is a surprising lack of understanding as to what really happens to the gear when it's fishing down on the seabed. This video film will give fishermen an insight into what happens to the gear as various alterations are made to it at sea. Twin rigging is a method of trawling that uses two nets side by side on the seabed. Two relatively small nets are used instead of one large net, because an equivalent area of seabed can be covered much more efficiently with two smaller nets. The usual setup is two similar trawl nets, 4 sets of sweeps and bridles, a pair of trawl doors to spread the gear, and a heavy weight, often called a clump. The purpose of the clump weight is to keep the center sweeps and bridles down on the seabed. There are two basic twin rig setups. One uses 3 separate warps. The other uses just 2 warps. The doors, clump weights, bridles and nets are similar for each setup. One of the main problems with any twin rig system is how to keep both nets square at all times. In both rigs, the tuning of the gear is normally done by alteration of the warp lengths. We shall look at the rigging of the gear to begin with. The first thing to ensure is that the rig is square. This means both nets should be similar. All 4 sets of bridles and sweeps should be the same length. The doors and clump, together with their associated chains and backstrops, should each be of equal length overall. This means that the distance from the towing point of the doors to the after point of their backstrops should be the same as the distance from the towing point of the clump to the after end of its backstrops. If the components are of equal length, then everything beyond the end of the towing warps is of equal length. Here we have an ideal situation. All 4 wing ends are in line. All 4 sets of bridles are in line. All 4 sweeps are in line. The doors and clump weight are in line. The doors are properly spread. This means that the nets are all symmetrical and in their ideal fishing position. But in order to achieve this, the gear has to be tuned. For the 3-warp rig, this is usually done by shortening up the center warp leading to the clump. This brings the nets and doors into line. For the 2-warp rig, it is more usual to add separate extension sections to the outside split warps. We are going to concentrate first on the 3-warp rig. Despite this rig having 3 separate warps, it is relatively straightforward to set up correctly. If we look at a 3-warp rig that has been shot with all 3 warps set at the same length. Here, the gear has been artificially held closed up to show that everything is of equal length. If the gear is now allowed to spread, it can be seen that, as the doors spread out and away from the clump, they describe an arc. The center of this arc is at the stern of the vessel. As the doors follow this path, they pull forwards of the clump weight. If we look at the nets when the gear is in this configuration, we can see that both are distorted, and the inside wings of both nets are hanging back. This creates a lot of slack netting, with open meshes in the inside quarter of the nets. If we look at the outside quarters of each net, we can see that the meshes are all closed up, with excessive strain on the netting. In this configuration, these nets would probably not fish very well, and would be liable to damage. So, how do we get the nets square? To square up the nets, the center warp must be shortened so that it pulls the clump weight back into line with the trawl doors. But how do we find out how much needs hauling in on the center warp? If we assume that all the warps are straight lines when the gear is all level and square, we can form a right-angled triangle between one of the outside warps and the center warp, together with half the door spread as the base of the triangle. We know the outside warp length from what has been paid away from the winch. By using acoustic sensors or the warp divergence method, we can measure the total door spread. Halving this value gives the distance from the clump, which forms the base of the triangle. This leaves the center warp as the unknown side of the triangle. Using the triangle, we can then calculate the required length of the center warp. To simplify this, Seafish gear technologists have produced a set of tables for finding the center warp lengths corresponding with a wide range of warp lengths and door spreads. Looking at the table, we can see there is a range of door spreads down the left-hand side. There is a range of warp lengths along the top. In this example, if we were fishing with 275 fathoms of warp out and a door spread of 350 feet, we would look down the 275 fathoms column and across the 350 feet row in the table. Where they intersect, we find a value of 9.3 feet. This is the amount that the center warp should be shortened by in order to bring the clump in line with the doors, making the nets symmetrical. Remember, the shortening of the center warp is based on the assumption that all 3 warps are straight lines. In reality, the warps leading to the doors will be more curved than the warp leading to the clump weight when the gear is square. This means that the shortening of the center warp needs to be very slightly more than the lengths in the table. We are now going to look at what happens when the center warp length is corrected for a 3-warp rig using models in the flume tank. We will go through the procedure of measuring the door spread and altering the center warp length accordingly to square up the nets. Here the nets are being shot with all 3 warps of equal length, and the doors are starting to spread the gear. As we saw earlier, as the doors spread, they pull ahead of the clump weight, and this causes the nets to distort. We can see this very clearly when the film speed is increased. In this example, we have the equivalent of 275 fathoms of warp out. We have measured the door spread at 250 feet. By consulting the table, we can see that in order to square up the gear, we should shorten the center warp by 4.7 feet. We will now haul in the center warp by the equivalent of 4.7 feet and watch the effect that this has on the gear. Here, the nets improve in shape, but they are still distorted. If we watch the doors as the warp is shortened, we can see that they are spreading more, allowing them to pull still further ahead of the clump weight. The reason for this is that as we haul in the center warp, we are taking up more load on it. Hauling in the center warp reduces the tension in the outside warps, and this allows the doors to spread out yet further. As the door spread has now changed, we have to measure it again and recalculate the shortening of the center warp, but this time using the new door spread. Our door spread is now about 300 feet. The warp out is still 275 fathoms. Using the table, we can see that the center warp should be 6.8 feet shorter than the outside two warps. It is already 4.7 feet shorter, therefore we need to shorten it again by the difference, which is 2.1 feet, to try to square the gear up. When we look at the gear now, the nets are still not symmetrical, because the doors have spread still further out. We have to check the door spread again. This gives us a new spread of 325 feet. Looking at the table, for 275 fathoms of warp out and a spread of 325 feet, we need a center warp shortened by 8 feet. This means that we must haul in the center warp by a further 1.2 feet. We now check the door spread once more and find that there is very little change. Looking at the gear, the doors and clump are in line. The nets are now square. This means that the gear is now in its optimum fishing position. It is good practice to check the door spread regularly. If at any time the warp length is altered or the door spread changes, the tables should be checked to make sure that the center warp is shortened by the correct amount. Using the tables is not a one-off process, but a gradual process whereby the final answer is homed in upon in stages. We now haul the center warp in by 2 feet more than that recommended in the tables. The nets are still in a good fishing shape, with very little distortion, despite the clump now being slightly ahead of the doors. It is not until the center warp is taken in by several feet further that the net begins to distort in the outer wings. This shows us that it is preferable to have the centre warp hauled slightly too much rather than not enough. As we shorten the centre warp, there can be a tendency for other problems to arise that may deter many skippers from shortening up the centre warp by as much as they should do. The first potential problem is that the centre clump weight could lift off the seabed if it's not heavy enough. The clump weight could also lift off the seabed when an inappropriate warp-to-depth ratio is used. The second potential problem is that the trawl doors become unstable due to the changes in the outside warp angle and warp tension. This could be due to the doors not being correctly matched to the twin rig nets and vessel. A third potential problem is related to fish behavior. The increase in door spread could create too great a bridle angle or too great a wing end spread for the target species of fish concerned. A correctly rigged 3-warp twin rig will provide consistent performance at sea and will minimize the risk of damage to the nets. Alterations to the length of the center warp are quick and easy to achieve, without the need for hauling the gear. In comparison, the 2-warp twin rig requires a different approach. In this setup, the nets, bridles, sweeps, doors and clump weight are rigged in a similar manner to that of a 3-warp system. From the nets to the trawl warps, everything is of equal length as before. The difference is that each of the main trawl warps divides into 2 split warps. The outside split warps are attached to their respective port and starboard doors. The 2 inside split warps are both attached to the center clump weight. These split warps can vary in length from 15 fathoms up to 125 fathoms. The length is dictated by the length of sweep and bridle used and also the door spread that is needed. If we look at a 2-warp rig with all 4 split warps of equal length, we can see that the nets are distorted. The 2 inside wings are slack and need to be pulled forwards to square up the gear. In the 3-warp rig, we did this by hauling in the center warp. For the 2-warp rig, it is more usual to square the gear by adding extensions to the 2 outside split warps. How do we know what length of extension to use? In the 2-warp rig, it is impossible to use the warp divergence method to calculate the door spread. This is because the port and starboard warps don't go directly to the trawl doors, but deviate where the split warps join onto them. Even using acoustic door sensors, it is still difficult to square up the gear in the 2-warp system. However, it is possible to calculate the spread at the end of the main warps. From this, we can work out a suitable length for the extensions that are needed in the outside split warps to get the gear square. This is a simplified calculation and will only generate an approximate result. As for the 3-warp system, a set of tables has been developed to enable skippers to estimate the extension needed to square up the gear. We need to have separate tables for each split warp length, because the geometry of the two-warp system alters considerably when changes are made to the split warp lengths. In this example, in the flume tank, we have the equivalent of 75 fathoms of split warps. We have a main warp length of 100 fathoms. If we measure the warp spread, that is, the distance between the main warps of the splits, we obtain a figure of about 90 feet. At sea, we can do this by using the warp divergence method. We now look in the table of extensions for 75 fathom split warps. For 90 feet of warp spread, and for 100 fathoms of warp out, we can see that the estimated extension length needed is 8.3 feet. When this 8.3 feet is added to the outside split warps, it will allow the trawl doors to drop back, thereby reducing the tension in the outside split warps and increasing the tension in the inside split warps. This allows the doors to spread more and may alter the geometry of the warps. For this reason, it is advisable to measure the warp spread again and check it against the tables in case a change in extension length is needed. Having added the extension and being satisfied that the gear is symmetrical, we can now look at the second part of the two warp tables to give us an indication of the door spread. This table can be used once the extension has been added to the outside split warps and the nets are square. Using our warp spread of 90 feet and our warp length of 100 fathoms, we get an estimated door spread of 285 feet. This figure is accurate enough to calculate the bridle angles and wing end spreads, if needed, to give a fuller picture of the gear parameters. There are many combinations of warp length, split warp length, and bridle lengths. Because of this, these setup tables often need tailoring to a particular vessel's requirements. In our flume tank test, we did several experiments using the same overall warp lengths, but used 3 different lengths of split warps. This was to simulate a vessel towing the same nets, sweeps and doors at a constant warp-to-depth ratio with different split warp lengths. In this situation, if we increase the split warps to 100 fathoms, the door spread increased to 312 feet, with an extension of 11.5 feet. If the split warp length is reduced to 50 fathoms, this restricts the door spread to 250 feet, using an extension of 6 feet. Once a skipper has tuned his two-warp setup, there is very rarely any need to alter the extension lengths, unless another part of the gear is changed. The extension needed in the outside split warp of a two-warp rig will normally be much less than the shortening of the center warp in a three-warp rig for a vessel towing similar gear. One of the main limitations of the two-warp rig is a reduced door spread compared with that of the equivalent three-warp system. This is due to spread of the doors being restricted by the relatively short split warps. As we have seen, the three-warp rig can be tuned while towing the gear, whereas the two-warp system needs to be hauled before alterations can be made. One of the main advantages of the two-warp rig is that it enables a trawler to tow a twin rig system using an existing two-barrel trawl winch. This can reduce the initial outlay required for changing to the twin rig by saving the expense of a new three-barrel trawl winch and rerouting of deck leads. However, a 2-warp system lacks the versatility of the 3-warp system, where the door spread can be tuned to suit different fish species by altering the center warp. In both the 2 and the 3-warp methods, the alterations obtained from the respective tables should be used in conjunction with any other indications of gear symmetry. Other indications can include meshing of fish and shellfish in areas of slack netting, distortion of the lower bosom meshes of the nets, distance and angle measurements from acoustic gear sensors. In this video, we hope to convey an understanding of squaring up the nets in a twin rig system using basic gear parameters that are available to all fishermen, no matter what the size of their vessel. Remember, the optimum tuning of a twin rig can be further enhanced if used in conjunction with any additional measurements made using acoustic gear sensors and tension meters. As the warp tensions within any twin rig system will vary considerably, the warps tend to stretch at different rates. To reduce errors in measurements and calculations, it is important that the warp lengths are checked regularly. It would appear that twin rig systems in general are much more tolerant to discrepancies than a single net rig. When compared with a single net, a twin rig tends to fish well even when the gear is not trimmed perfectly. This video film has provided an insight into the setup of a twin rig trawl and what can happen to it when rigging changes are made. Having a correctly tuned twin rig setup, either a 2-warp or 3-warp system, means that the gear is fishing at its very best. This means less risk, less time wasted, and better fishing opportunities.